All right, so today we're going to be looking at moving to our next assignment, if you would, or next phase in our gearbox, and that's going to be looking at shafts. Up in our learning plan here, in our gearbox project overview, I've added some things here for our session number 3. So the first thing you're going to notice is there is a gearbox shaft design, and I have all in back of it. You're going to want to download that Excel spreadsheet. You're going to find that what I did was I added tabs for all 3 shafts on the bottom. And then that way it's one spreadsheet rather than having 3 separate ones to deal with. Okay, so we'll look at that. Additionally, you're going to notice down here, we're going to be talking a little bit about bearings today too, because they're kind of the next logical thing to do. There's a new bearing spreadsheet there as well. I'm going to download mine right away. And again, this is going to be because we need to specify 6 bearings rather than having 6 separate spreadsheets. Let's just put them all on the same spreadsheet. So I'm going to go through how those are set up as well. So these are going to be our focus for today. Session number 3 is dedicated to overview of shaft design and then the overview of the bearing design. Okay. So what I'm going to do is I'm actually going to go over to our assignment. I wonder if I can go back. Maybe I can go back one level. Yep. I'm going to go to our assignment for shafts. And you're going to notice here that on the top here, for shaft design deliverables, you're going to do everything in the Excel spreadsheet. Okay. So if you open up that Excel spreadsheet, if you happen to download it, you're going to want to open up the Excel spreadsheet. Go to open, and I'm going to browse to my downloads, and it should be over there. Oopsie, shaft design. There we go. And something that's different about this spreadsheet compared to our original that we used in our assignment for module number 6 is that you'll notice right at the bottom here, we have all 3 shafts identified. So the yellow tabs are going to be the input shaft, which is our first one. The blue tabs are going to be the jack shaft, which is that middle shaft. And then if we go all the way to the right here, the green tabs at the bottom are going to be the output shaft. Okay. Now you'll notice that there are 3 tabs for each one of our shafts. The 3 tabs are going to be just like what we had used in module 6. So the first tab is going to be sheet 1 for the input shaft. And then sheet 2 is going to be those minimum shaft diameters. And then you're going to have a place for the summary of your results for that shaft. So that's going to have your, a picture or a scanned, view of your torque diagram, your conditions diagram, the MD solid screenshots. You can put those all in here. And we'll look at the other things we want to put in this design summary, but that'll be just for the input. Then you're going to have the same 3 tabs for the jack shaft. And then you're going to have 3 more tabs for that output shaft. And this way in one file, you've got all 3 and you don't have to try to pull up different spreadsheets and wonder where you're at. Okay. I've already got them set so that, for instance, your endurance strength comes from the output shaft sheet 1. Okay. And then the same thing for the jack shaft. You'll notice that endurance strength for the jack shaft comes from the jack shaft sheet 1. So you shouldn't have to mess around with anything that way. So I wanted to show you that this is really the same spreadsheets, the same formatting. But again, instead of having only 1 in a spreadsheet, you've got all 3 in 1. Okay. Now, let's go back to the assignment because this kind of walks you through what you'll be doing. So it says here, the Excel spreadsheet file is going to include the input jack and the output shafts. And there's this, the Excel spreadsheet with all 3 of those on right here for you to download. Now on your summary of results, which is that 3rd sheet or that 3rd tab, you're going to do the following. You're going to have the shaft details table shaft details table for that shaft. So I want to know what is the material that you picked for that shaft. You can have different materials for each one of those shafts separately. They don't all have to have the same shaft if you didn't want them to. I would probably start there, but you're going to call out that. Then you're going to tell me what was the minimum shaft diameter for each of the critical sections. Most of those sections, you're going to have to do a left and a right calculation, but the larger of the two is going to be your minimum shaft diameter. So what was that exact number for each one of your sections? Then you're going to round those up to basic nominal values. And I want you to then have a column that's going to tell me what that was for that specific section. Then you're going to have a column for your shaft to gear tolerance class of fit. And then the shaft to gear tolerance limits for the shaft. We're going to be talking about that in just a bit after we go through this. Then you're going to have a column for shaft to bearing limits. Now you'll notice there's an asterisk here. That will be filled in after you do bearing design. Okay, so you won't be able to fill that in right away, but once you do bearing design, you'll be able to add that in. Same thing here for nominal key size, key seat width limits, and also the key seat depth limits. Those are going to be filled in when we do our keys. So those last four columns, if you would, in a table that you create are going to be filled in. So they'll be empty right now until we get past those items. And then you'll notice there's screenshots for the following. So you're going to have 3 proposed shaft designs. So what that means is that's going to be your critical diameters. At the very beginning of the chapter 12 in your book, the on page 512, this is where they propose the geometry of how they're going to keep things in place. So where are your retaining rings? Where are your shoulders, sharp radiuses, that type of thing, because that's going to then guide you, as you know, as you work through the design for KT values, the conditions diagram, all that kind of stuff. So that's what that's speaking of. Now, some of you, if you wanted to do that in AutoCAD, you certainly may. It can be a sketch, I don't mind, but then just make sure that it's a nice sketch that's, and I have, I think, a little note down here. You must use straight edges and neat handwriting. Okay, this is considered, you know, it's probably not formally your capstone project, but it's in your last semester. You've done some things. It can be used as, you know, an article of proof when you go interview for jobs that you have done this type of design work. Okay, and it's going to be an example of the type of work that you do. So you want this to be nice and neat. Okay. Then you're going to have 3 sketches of your shaft forces and bearing reactions. These are your hand-drawn free body diagrams where you put on the shaft in relationship to your bearing supports as well as the forces that the gears are generating. Okay. And then those are the sketches that you use then to create your MD solids. So for each one of these shafts, you need 2 views in MD solids, right? Our front and our top view essentially from the previous step there, but 6 total, 2 for your input, 2 for your jack, and 2 for your output shaft. Okay. You're going to have 3 torque diagrams. Each one of these is going to be on their respective summaries page. You're going to have 3 conditions diagrams. And then I have here too, if you want to do it in CAD or hand sketch, totally up to you. AutoCAD lends itself really well to these types of items, but I'm not going to require you to do that, but it does look really nice. It does look really nice. And then I want a sketched CAD drawing. Now this again is layout form. This is not a formal dimensioned release for production type of a drawing of a shaft. All this is to identify your basic sizes in relationship to the length of the shaft so that you can see that you designed it so it's assemblable. Okay, so that's what that's there for. No tolerances, just basic sizes for that sketch. Okay, it's again kind of summarizing what your final results are. Now, and again, using Excel, we just already saw the spreadsheet itself, and all of these things can be put into that 3rd tab for their respective shafts. Okay, any questions so far? All right, let's look at fits. Okay, let's look at fits. You'll notice here that on your spreadsheet, you need to add and you need to specify shaft to gear tolerance or tolerances, your class of fit, and then the appropriate tolerances. So I wanted to review where we see it in this machine elements book, but then also this process is something that you've seen in previous classes that we're going to be reapplying here. Okay, so underneath my camera, you're gonna find that the tolerance tables are in chapter 13 in your book. And actually, I'm looking at page 551. Now, we will be looking at this chapter in detail, actually right after we're done with this project, but in a little bit different form. For this project, we're going to be using it to determine what our appropriate clearance fits are going to be for the elements, mounting the gear to the shaft, okay? But when we look at like force fits or press fits, there's going to be stress that's going to be induced. And so in our module 5, so we kind of are going out of order. We went 4, 6, 7, and then we're going to go back to 5. In module 5, we're actually going to be calculating the stress that's generated on press fits and then making sure that it's not exceeding the yield strength for that material. But that's not what we need here for this project. We're just going to be using those standard fit tables to determine what the limits of the tolerances would be to get our gear appropriately, fit to our shaft. Okay. So I wanted to go over and review how to do that. Now, in section 13.5 here, clearance fits. Okay. Clearance fits. So a clearance fit is going to be when we can freely put one item onto another. Now, most often we talk about in terms of hole and a shaft, but this doesn't have to be a circular feature. It's just really an internal and an external feature, if you would. So, so when we're using ours, it is going to be a bore, a hole in that gear that's going to have to fit over the top of a section in the shaft. Okay. So, so you'll notice that the fits that are for clearance fits, they're called RC fits. That's called a running clearance fits. That means that when I put them together, there's always going to be at least a little bit of a gap. Okay, a little bit of a gap. And there's a whole series of fits, and they start at RC1, which is called a close sliding fit, all the way to RC9, which is a loose running fit. Loose running fit. Now, in the descriptions that you have here, you're going to notice that they kind of give you some, a little bit of information so that you can make a decision about where they're actually going to be used. Okay. So you'll notice that in an RC1 fit, this is a close sliding fit. This is for accurate location of parts that must assemble without really any play. Okay. They're going to go together. You're almost like probably tapping them on. All right. Then as we go up a couple, RC3, this is a precision running. This is going to be precision parts operating at low speeds and light loads that must run freely. Changes in temperature could cause difficulties, meaning that, if we get a little bit of expansion, they're going to be like tightened up and probably, at some level, a little bit of a press fit. Okay. As we look to an RC5, this is a medium running fit. I think this is probably the one that's most appropriate for what we're looking at. Accurate machine parts for high speeds and or loads, little bit more than an RC4. You'll notice that down on the charts that you have here, they don't have columns for all 9. If you find that you feel yours would fit into a different category, the Machinery's Handbook, and I can go get mine. I think there's one in the room here as well. The Machinery's Handbook has all of the categories listed, and these are out of there. Okay, but the book did RC2, RC5, and RC8 just to get, a couple different levels here. All right. I think an RC5, or if you wanted to, an RC2, I think would be appropriate. But again, this one, if you read the description, you can have a little bit of expansion could cause things to get tight. And then you can read the other one. So my question to you, because you guys didn't have me for GD&T, and I'm confident that Phil would have covered this. Do you guys remember these charts and picking out fits? Okay. Okay. Yeah. Oh, yeah. So you would have had like 3 choices like this, right? Yeah. Yeah, and that's okay. The in-betweens, they don't have in this book either. Your full list would come from the Machinery's Handbook. Go ahead, BJ.
I was going to say, it was like, we had either like interference fit, clearance fit, or press fit.
Those are the 3 main categories of fits.
That's all.
Oh, okay. All right. Well, then what we'll do is we're going to go over this because this is it's not hard. It's really actually really easy. What was that? Yes, we're gonna assume ambient temperature, yep, all the time, and that we're not gonna have any issues. So what we'll do is, let's go over an example, okay, to make sure that you understand and to review this. I have a feeling you might have hit this at some place and you're just maybe, well, I don't know. I'm thinking you did at some point, but that's okay. So, what you need to start with first, we're gonna look at this chart, and these charts are set up exactly the way you're gonna notice them in a more expanded form, like in the Machinery's Handbook, for instance. On the furthest left-hand column here, you have a nominal size range, okay? And this nominal size range is going to give us over 0 to 0.12. That's what's included in this row right here. So if your nominal size lands in there, so for instance, a 1/16 of an inch in diameter would land there, that would be the row you're going to work with, okay? So the doesn't matter. The external, it says your nominal size of your shaft or the bore of your gear. Okay, so let's say we determine that our basic size on our shaft is 1 inch. Okay, that means that the nominal size or the basic size of the bore in the gear has to be 1 inch. But now we have to tolerance them to fit together so that they'll always fit together. So if I look down here, I want to find where my 1 inch falls, and it falls right here between 0.71 and 1.119. So this is going to be my column. All right. Now I'm going to work, like I said, with the RC5 fit. So down here, these 3 middle columns are going to, 3 middle columns are what I'm going to be focusing on. Okay. And they have numbers here. So within those 3 columns, you're going to notice the first column on the left, it says limits of clearance. So when I put these together, this is the range of clearance that I'm going to have when I show the extremes, if you would, for the shaft and for the bore on the hub. And those limits of clearance are going to be 1.6 to 3.6. Now, that's not inches, okay? If we go down to the very bottom of this chart, and this is the same case for the ones in the Machinery's Handbook or any that you're going to find, there's a little statement down here and it says limits are in thousandths of an inch, thousandths of an inch. So I'm going to take those values. Okay, they're right here. So my nominal size is 1 inch, 1 inch. Go, stand up, bless you a little bit. 1 inch. And you'll notice that my limits of clearance are 1.6. So I'm going to put limits of clearance. I've got 1.6 to 3.6. All right. Now that's thousandths of an inch. So an easy way to do this is to simply move my decimal place 1, 2, 3 to the left, thousandth of an inch. Okay. And all that's going to be is these are the zeros that then are in front of that number. Does that make sense to everybody? Oopsie, I have an extra 0. Sorry. The 1 would be here. So I go 1, 2, 3. So 2 zeros. So the actual number that this is going to be, the clearance is going to be 0.0016, small number, okay, of an inch. And then the same thing here, 1, 2, 3. So I put my decimal here, 2 zeros in front of that, and this is of an inch. So that's how much clearance. So the maximum clearance that I'm going to see, or my slop when I have them together, is going to be 0.003, almost not quite 4 thousandths of an inch. And then when I'm at my, my smallest clearance, the minimum clearance, it's going to be less, and it's going to be just over 1,000th of an inch, almost, between 1,000th and 2. Okay. All right. So every number in here is to the 1,000th of an inch. So now that's the limits of clearance. That's the high and the low value, the amount of, if you would, slop that I'm going to have when I have these together. Now, if I go back here and I look, you're going to notice that there is a column for the hole limits and for the shaft limits. You don't have to do any work here except accurately specify these. So for the shaft, okay, my nominal size is 1 inch. So I'm going to look to my shaft column, and it says 1.6, negative 1.6 to negative 2.4. Okay, so what I'm going to do is I'm going to put negative 0.0016 on top here, negative 0.0024. And what that means is now I am going to subtract 1 minus 0.0016 for the actual limit. What do I get for that number? Let's do that math. Everybody should have their calculator out. Yep, 0.9984. Okay, and then we're going to do that for the very same thing for that bottom number. Those are the limits on your shaft. Those are what you're going to populate that column that you have on your summary of results, where I said shaft to gear tolerance limits. You're gonna list your class of fit. This would be an RC5. And then you're going to put your shaft to gear tolerance limits, 0.9984 to 0.9976. That's what you're going to put in there for that. And then when we get to shaft with the bearing, the keys, they're going to do the same thing. So just make sure that you add a column for each one of those, because then they'll continue to populate those as we come up against those parts of the project. Okay. Now, if you recall, we go back to one level here, and we go back to our gears, gearbox gears. You're going to notice that you have a place here where you're going to have to put the bore limits, tolerance limits to fit the shaft. This is where you're going to do that. Okay. So let's go back and using this 1-inch example. Okay. For my gear, then I'm just going to turn this over just so that I have space here. I'm going to go on that same row, but for my gear this time, my nominal size is still, we're going to do 1 inch. Okay. And now my gear has the hole in it. That's the bore that has to fit over the top of the shaft. And this one is plus 0.0012 and minus 0. Okay. So now we simply have to add this limit over here. My limit is going to be 1.0012 to 1.000. Okay. Those are the limits then that you're going to add to the gear. Okay. Now, we're not going to be making the final detailed drawings, but this is, like I said, right up before we are actually going to do that, right? And release. So you would need to know what your tolerances are, and we're picking those, you know, as part of this project. Okay. So now you know. Now, I have a question for you. Do you notice that the nominal size 1 inch is in the bore? See that? And here, my nominal size doesn't land in my actual limits. Why do you think that is? Why do you think that is? Why is my nominal size? Yeah. They wouldn't go together, but think. There you go. Tools that we're going to be using to make these features, to manufacture them. You can get a drill, a boring tool that's going to be 1 inch nominal, right? And on a shaft, I can simply go in and out with my tool on a lathe, right? And I can make it smaller or larger to whatever number I need it to be. So this is called the basic hole system. And that's how all of these charts are set up, so that your nominal will always be on the hole size, right? Okay. So I just wanted to point that out, because that's, I mean, it's kind of important, you know, to kind of know that, especially when we're using things like, you know, tools that are going to be standard sizes. Okay. So that standard size is hitting the bore in this case. Okay. All right. Now tell me, have you guys done this before? Or don't you feel like you did? You still don't feel like you did. Oh my gosh. Okay. All right. I have to believe you have. If not, then you got it. But this is important, because whenever you have parts that are fitting out in industry, in your designs, in your capstone project, you don't have to like figure it out yourself. We've got charts that help us do that. And what's great is they have it figured out, you know, like what is the type of fit that you want. They give you a nice description. Then you put your, you know, function into that category. And now you can just get it right from a chart. Okay. You can. The best way to do it, especially when you're working with 4-place decimals, is don't let somebody add and subtract it in their head. you would actually put the limits on the drawing. The high and the low limits for that diameter. That's really the best way to do it. You want to always think of who's going to be making this. And if I let it up to, you can do a minus and a minus, that you can do that. But remember, this requires somebody to do that math in their head on a calculator. And there's a step in between there where in translation, you might not get the actual numbers. So especially when you have things that are really accurate, on the drawing is where you would want to actually put the limits. I wouldn't, again, for that reason. Yeah. Other questions? All right. Oh, I got a chat. Hold on. I missed it. I hope I didn't miss it. I remember doing it with Tom in AutoCAD class. See, there you go. Yeah. If you had me for tech drafting, you would have done it with me too. And then I know I'm going to do it in GD&T and you know, we want to sprinkle it about, but it comes up here, you know, when you start putting things together like shafts and bores of gears. Okay. What are my numbers, right? You can't just put 1 inch plus or minus 5 on one and 1 inch plus or minus 5 on the other, because you're going to have interference. You might have clearance sometimes, but sometimes you're going to have interference and that's not going to work. So these have it all figured out for you. Okay. What was that? Of course. You always have size dimensions. The GD&T is going to come into play when you have position tolerances. You still always have size. So this is the size, but you still need size. Every one of and this is your size dimension. And then you can add to it what you need for either position, straightness, you know, all the things. Run out, you could put on here, not concentricity anymore. You know why? Do you guys do concentricity? They took it out. Yep. Yeah, no new drawings get concentricity anymore, and you should fix up your old ones. What was that? That's for another day. We're not doing GD&T today, but it's comparing one axis to another. One axis to another. Axis to axis is what concentricity is. Yeah. So any other questions about picking out these tolerances? Okay. So if it is something new, it's pretty straightforward, but if you did want me to come around and just check with you on, you know, on how you're doing and make sure that you're on the right track, I'm happy to do that. So just want you to know, page 551, it's not a chapter that we've gone over just yet. We will get there, but yeah, this is where the chart is that you can use for specifying the limits of size on the bore on your gear, and then the shaft diameter where that gear is going to mate. Okay. All right. All right. Let's go back over here. I'm going to go. So that's going to be that one. And then I still have the gear assignment up. Remember, we're going to have the keyway nominal size. That'll be part of that one. All right. So let's talked about screenshots. Let's take a brief look at the spreadsheet for shaft design. Okay, for shaft design. So you're going to notice, I'm going to go to the very beginning here. Again, the colors kind of clump them together. The first one is going to be the input shaft here. Okay, scooch this over a little bit. And these are the very same spreadsheets that we used. Okay, so nothing new here. So sheet 1 is going to be all of your inputs. This is where you're going to be picking your material, your yield strength, and then you're going to be, you know, adding the figures from chapter 5, and then you'll get a modified endurance strength. On your second sheet, your modified endurance strength will then automatically populate, as well as your yield strength and such wherever the calculations need it. So if you end up moving anything around, then you've just got to make sure that you check to make sure that you still have the things populating where they're supposed to. On that first sheet, you have your torques as well that you're going to be calculating, or you can use to calculate. And then for our gearbox, the only forces that you're going to be really interested in for any one of the shafts is going to be gears. Our chain sprockets and the V-belt shivs, I have them on here, but they won't be used because they're not elements that we're incorporating into our design. Then you've got sheet 2, where you're going to have all of your categories for the different types of conditions that are present at the different elements. So this is going to be where you have your torque and bending, And then going down, you have vertical shear only, torque only, and then your bending only, sorry. Okay. And then you're going to have your input shaft summary results. And then this one is blank right now for you to fill in based on what we had just looked at criteria wise. Okay. And then the blues are going to be the jack shaft. And then, like I said earlier, the greens are going to be that output shaft. Any questions spreadsheet wise? Okay. All right. So that should all be pretty familiar. In module 6, you guys practiced using this a lot. You would have, before you get here, you have 4 designs, if you would, under your belt. But it's a long process. It's a big process. If you have any questions as you go along, that's what I'm here for. Okay. So as we look at shaft design, this is going to be due then next week. Okay. Because of the fact that, let's see, I'm sorry. Go over here because of the fact that there's some things that you won't be able to fill in yet. So for instance, on the shaft design, we have to have our bearings done to put the bearing tolerances in. We have to have our keys done to put the key, width, height, and depth in. So those are going to be empty places that once they're filled in, then we'll have the shaft design due so that it's complete. Okay. So that's the shaft design portion. Any questions right now? Okay. All right. Then what I'm going to do is I'm going to stop recording.